Welcome to the AI Research Roundup. I am Alex. Today, we're looking at a new paper from May 22nd, 2025, trending on Papers with Code, titled Training Free Efficient Video Generation via Dynamic Token Carving. This work introduces Jenga, a novel pipeline to make high-quality video generation much faster. It tackles the intense computational demands of current video diffusion transformer, or DIT models. These video diffusion transformer models create video by gradually refining noise over many steps, and they process a lot of data. Jenga cleverly optimizes this by not requiring full detail in early steps and using a more focused approach later on, all without retraining the original model. And for those looking to try this out, it's great to see they've also released the official implementation. So over on GitHub, you'll find the Jenga code for this work. It's got scripts for inference, which is the process of using the trained model to generate new videos on single or multiple GPUs, along with environment, setup guides, and model download details. This makes it easier for other researchers and developers to use and build upon Jenga. Alright, so this first figure really gives us a great visual of what Jenga achieves. We see some impressive examples of high-quality videos, like a cat and even a woolly mammoth, alongside the significant speedups Jenga offers. Part A of the figure, with the pandas, makes the point that Jenga's intelligent, sparse attention aims to preserve details without the content degradation that naive heavy pruning might cause. Then, Part B shows its core idea of reducing token interactions. Tokens, which are small pieces of video data, are used sparsely in early denoising steps. That's the video refinement process, and more densely later for fine details. This progressive approach is key to Jenga's efficiency. Okay, so building on that idea of reducing token interactions, this next figure dives deeper into one of Jenga's core techniques called attention carving. On the left, it shows how the model first takes the 3D video data, which are called latents, essentially the intermediate learned features of the video, and reorders them. It uses what's called a space filling curve, a smart method to arrange these 3D data points into a 1D sequence, helping to keep nearby elements together. Then, these reordered latents are grouped into blocks. On the right, we see how Jenga then selectively computes attention. Attention is the mechanism that helps the model weigh the importance of different data blocks to each other. Instead of looking at all blocks, it uses specific masks, an importance mask for the most relevant blocks, a condition mask to ensure text prompts are properly handled, and an adjacency mask to include neighboring blocks, which helps maintain smooth transitions and avoid visual artifacts. This blockwise approach is what makes the attention process much more efficient. Alright, so this provides a broader look at the Jenga pipeline. The left side visually summarizes that attention carving technique we just discussed, with the 3D video latents being partitioned and then undergoing selective blockwise attention using masks. The new element detailed on the right is Jenga's progressive resolution strategy. You can see how the video generation starts at a lower resolution, say 360p, focusing on the main content, and then progressively increases to 540p and then 720p to fill in the finer details. This multi-stage approach significantly cuts down on computation in the earlier phases. Okay, so we've seen how Jenga uses progressive resolution in general. This gives us a closer look at how that actually works. The top left part shows the multi-stage latent rescale. So at the end of each stage, say stage S, the model predicts a clean version of the video latent. This clean latent is then upsampled, or increased in resolution, and then a bit of noise is added back before it goes into the next higher resolution stage, like S+1. Then, on the right and bottom, it details the text attention amplifier. This is pretty neat, because when you generate video at lower resolutions, you can sometimes lose the broader context, an issue called field of view, or FOV degradation. The field of view is essentially how much of the scene is visible. To counter this, Jenga adds a small adjustment or bias to the video text attention scores, which helps the model maintain a consistent and wide field of view even when starting from a low resolution. Alright, so after seeing the mechanics of the text attention amplifier, here it gives us some visual proof of how well Jenga performs. Part A lines up Jenga against other video generation models. You can see examples like a fluffy monster or an octopus, and Jenga Turbo, a faster version of Jenga, generates these scenes much quicker, in around 220 seconds, while still capturing the core meaning of the text prompts. Then, Part B specifically shows the impact of that text attention amplifier we just talked about. It demonstrates how, even when Jenga starts generating a video at different initial resolutions, like 360p or 540p, the final field of view remains consistent and broad, which is exactly what that amplifier is designed to achieve. Okay, so after those visual demonstrations, here really quantifies Jenga's performance. It compares Jenga with other methods on the Hunyuan video model. We're looking at computational loads, measured in pflops. That's peta floating point operations per second, a unit indicating raw computing power, where lower values are better. Then there's quality evaluation using vbench, which includes metrics for overall quality and semantic coherence, plus clip score for text alignment. Higher scores are better here. And finally, latency and speed. Jenga Flash notably achieves an impressive 8.83 times speedup and much lower pflops, while maintaining competitive quality. This really drives home the efficiency from its attention carving and progressive resolution. Alright, so Reader showed us Jenga's core efficiency. Now, Cine, which is the top part of this, Cine delves into how Jenga adapts to different models and how it performs with parallel computing. Part A shows Jenga applied to Hunyuan Video I2V and WAN 2.1 models, achieving significant speedups, for instance, over 4 times faster, while keeping vbench scores very close to the originals. Part B then demonstrates Jenga's scalability, showing a Jenga 8 GPU setup achieving a remarkable 13.41 times speedup on a distilled model. Below, the bottom part presents a user study. This is where humans rated the videos. Across visual quality, semantic quality, and overall quality, Jenga variants were often preferred or rated as similar to slower, more computationally intensive methods. For example, Jenga Base was preferred over the standard Hunyuan video in overall quality by a noticeable margin, even though Jenga Base is much faster. This really underscores that Jenga's speed doesn't come at a huge cost to what people actually see and understand. As we've seen from those user studies and the earlier metrics, Jenga really offers a compelling way to generate videos much more efficiently without a major hit to quality. The key ideas of attention carving and progressive resolution are clearly very effective. This kind of work is crucial for making advanced video generation practical for more applications and users. Well, that's all for this AI Research Roundup. Thanks for tuning in, and I'm Alex.